Hello viewers, today in this program I will explain you an important concept of tracing a curve. A polynomial curve can be traced by using some points wise procedure. I will explain you a point wise procedure and importance of the curve tracing as a curve of the polynomial form can be traced using the pointwise procedure, and its importance can be discussed as follows. A curve tracing of a curve is very much useful to know the approximate shape of the curve. To find approximate shape of the curve, we analyze some important characteristic of the curve like symmetry, its asymptote, intersection with the axis and region of the curve, etc. The approximate shape of the curve give important information in finding the arc length, area and volume bounded by the curve. Therefore, the tracing of the curve is very important in the differential equation and differential calculation. Tracing of curve whose equation is given in the Cartesian form, that is f of x y is equal to a naught y n plus a 1 y n minus 1 x plus a 2 y n minus 2 x square and so on up to a n x n plus y n minus 1 and so on, that is a polynomial form of the equation. This equation represents a plane curve. To trace this type of curve, we analyze following characteristic of the curve. Number 1, symmetry. Number 2, position of origin. Number 3, point of intersection with the axis. Number 4, its asymptotes. Number 5, the sign of dy by dx. Number 6, sign of d2y over dx square, and at last reason of existence of the curve. Now I will explain you these points one by one for getting a clues for tracing of the curve. Number 1 is symmetry. If a curve, equation curve f x y is equal to 0 has only even power terms of y, then the curve is symmetrical about x axis. For example, y square is equal to 4ax, well known parabola. You all know the parabola is traced in the shape which is symmetrical about x axis. Similarly, if the equation of the curve f x y is equal to 0 has only even power terms of x, then the curve is symmetrical about y axis. For example, x square is equal to 4ay, that is again equation of parabola with a symmetry with y axis. Third, if a equation of the curve f x y is equal to 0 remain unaltered after interchanging x and y, then the curve is said to be symmetrical about the line y is equal to x. For example, x square plus y square is equal to x cube. Here, if we change x and y, then equation remains same. Therefore, it is symmetrical about the line y is equal to x, that is line of 45 degree as shown in the picture. If the equation of the curve f x y is equal to 0 remains same after changing sign of x and y, the curve is said to be symmetrical in opposite quadrant. That is, if it is having curve in first quadrant, the same will be having in the third quadrant as shown in the picture. And the example y is equal to x cube, if we change the sign, again we find y is equal to x cube. Now I will explain you the position of origin and its importance in the curve tracing. If f x y is equal to 0 satisfy the origin 0 0, the curve is passes through origin. If curve passes through origin, we find tangent at origin. Tangent at origin can be obtained by equating the lowest degree term of the curve equal to 0. The following example shows different kind of tangent at origin. Example 1, x to the power 4 plus x to the power 3 y plus y to the power 4 plus x plus y is equal to 0. This equation has lowest degree term as x plus y. If we equate them equal to 0, the tangent at origin is x plus y is equal to 0. This is single tangent. Similarly, example 2, x 4 plus x square y square plus y 4 plus x square is equal to 0. In this equation, the lowest degree term is x square. If we equate it equal to 0, the tangent at origin gives x square is equal to 0, that is x is equal to 0 twice. It represents double tangent at origin, but both the tangent are same. Therefore, there is cusp at the origin, cusp as shown in the picture. Example 3, x to the power 4 plus x square y square plus y to the power 4 plus x square minus y square is equal to 0. This equation has lowest degree term as x square minus y square. If we equate this equal to 0, we find the tangent at origin as x square minus y square is equal to 0, that is y is equal to plus minus x. We have two real and distinct tangent at the origin. It is called double tangent at origin. Both are real and distinct. Then there is node at the origin. Node is shown as in the picture. Example 5, x 4 plus y square x square plus y 4 plus x square plus y square is equal to 0. This equation has lowest degree term as x square plus y square. If we equate it equal to 0, we find tangent at origin as x square plus y square is equal to 0, that is y is equal to plus minus iota x. This is double tangent, but both are imaginary. Then the origin is isolated point. We cannot trace the curve at the origin. Origin is set isolated as shown in the film. Now I will explain the third point of which help the tracing, that is intersection of the axis. First we find the point of intersection with x axis by putting the y is equal to 0. In the given equation, we find the value of x. Let us suppose x is equal to a is the point where y is equal to 0. Then we have a point a comma 0 as the point of intersection on the x axis. We shift the origin to this new point a 0 by putting x is equal to x plus a in the given equation and equating lowest degree term now to 0. We find tangent at new origin, which help us in tracing of the curve. Similarly, for y axis, we put x is equal to 0 in the equation f x y is equal to 0 and find the value of y. Let us suppose y is equal to b is a point where the curve meet the y axis. Then we have 0 b as the point of intersection on y axis. We shift the origin to this new point 0 b and then find the tangent at the new origin by equating lowest degree term. For example, y is equal to x minus 1, x minus 2 is a given curve. Here if we put y is equal to 0, we find x is equal to 1 or 2. Shifting origin to 1 0, equation 1 becomes y is equal to x plus 1 minus 1 and x plus 1 minus 2, that is y is equal to x into x minus 1. Equating the lowest degree term, we find y is equal to minus x as tangent at new origin x is equal to 1. Similarly, by shifting to the point 2 0, we find y is equal to x as tangent at new origin 2 0. Similarly, by putting x is equal to 0 in the equation 1, we find y is equal to 2, that is the point of intersection on y axis as 0 2. Equation, if we shift the origin to 0 2, equation becomes y plus 2 is equal to x minus 1 into x minus 2, that is y plus 2 is equal to x square minus 3x plus 2. Equating the lowest degree term to 0, we find y is equal to minus 3x as tangent at new origin to 0. Now, I will explain you the fourth point which help the tracing as asymptote. An asymptote of the curve is a straight line which touches the curve at infinity. So, the branch of the curve near the asymptote is like parallel line. Asymptote parallel to x axis can be obtained by equating the coefficient of highest power terms of x in the given equation to 0. If this coefficient is constant, curve does not have any asymptote parallel to x axis, as shown in the example. The example here is x square plus 7x square y plus y cube plus 3x plus y is equal to 0. Curve does not have any asymptote parallel to x axis, while the curve x square y plus x cube plus y cube plus 7x plus 3y is equal to 0. This curve has x cube y plus 1 plus y square plus 7x plus 3y is equal to 0. It has y plus 1 as the coefficient of highest power term of x, that is x cube. Therefore, we have an asymptote y is equal to minus 1 which is parallel to x axis. Similarly, asymptote parallel to y axis can be obtained by equating the coefficient of highest power term of y to 0. If this coefficient is constant, curve does not have any asymptote parallel to y axis as shown in the example. This example is y4 plus 7x square y square plus y cube plus 3y is equal to 0. The highest power term of y is y4 and its coefficient is 1. Therefore, this curve has no asymptote parallel to y axis, while the curve x square y square plus x cube plus 3x square y minus 3y square is equal to 0. It is represented as y square x square minus 3 plus x cube plus 3x square y is equal to 0. This curve has two asymptotes parallel to y axis as x square minus 3 is equal to 0, that is x is equal to plus minus 3 are the asymptote parallel to y axis. Now, we find oblique asymptote if exists by general method of finding asymptote. For example, xy square minus 5x square y plus 6x cube plus 5y square plus 7x is equal to 0. This is homogeneous function x y of degree 3, 2 and 1 as are as respectively x y square minus 5 x square y plus 6 x cube. These are the terms of 3 degree, and the second degree term is 5 y square, and the single degree term here is 7 x. Putting y is equal to m, x is equal to 1 in various degree term, we find phi 3 m is equal to m square minus 5 m plus 6, phi 2 m is equal to 5 m square, and phi 1 m is equal to 7. Let asymptotes are given by y is equal to mx plus c, where m is given by phi 3 m is equal to 0, that is m square minus 5 m plus 6 is equal to 0. This implies m is equal to 4 and 3. Now, the c of the equation of the asymptote is given by c is equal to minus phi n minus 1 m upon phi n dash m, which is equal to minus 5 m square upon 2 m minus 5. For the value m is equal to 2, we find c is equal to 20, and for the value m is equal to 3, we find c is equal to minus 45, and the asymptotes are y is equal to 2x plus 20 and y is equal to 3x minus 45. This procedure I have explained for finding asymptote of the curve. Now, I will check the sign of dy by dx. For the given curve f x y, we find dy by dx. If in the interval a b dy by dx is positive, then the curve is increasing in this interval, and if dy by dx is negative, the curve is decreasing. So, the sign of dy by dx represents the increasing or decreasing sense of the curve in a given interval. Similarly, we will check the sign of d2y by dx square. For the given curve f x y is equal to 0, find d2y over dx square. If in the interval a b d2y by dx square is positive, then the curve is convex in this interval, and if d2y over dx square is less than 0, the curve is concave at the interval. If d2y over dx square is equal to 0, the curve has point of inflection at the point. Now, I will explain you the reason of existence of the curve. If the equation of the curve f x y is equal to 0 can be represented as y square in terms of x, then for the reason of existence of the curve, find the value of x which gives real value of y. If for some value of x there is no real value of y, then curve does not exist at this point. This is very important point of curve tracing, which gives the clue about the existence of the curve. Since the curve is in terms of y square must be positive for any value of x. If y square is negative, then curve does not exist. For example, y square is equal to x multiplied by x minus 1, x minus 2 whole divided by x plus 3. In this example, we find for x between 0 and 1, y square is positive. Therefore, curve exists in the interval 0, 1. Similarly, from 1 to 0, y square is negative, so curve does not exist. For x greater than 2, y square is positive, therefore curve exists. Similarly, for x less than minus 3 and greater than 0, it is negative, curve does not exist. And now if x is less than minus 3, y square is negative, so curve does not exist. This shows the existence of the curve in different part of the surface. Today in this program, I have explained an important concept of curve tracing. I have explained a pointwise technique which help us to trace a polynomial curve. The procedure consists of 7 points, as number 1 I have discussed about symmetry about x axis, y axis, or about the line y is equal to x, or about the opposite quadrant. Then I have explained the position of origin. The position of origin and tangent at origin gives us a very important clue about cusp, node, or isolated point as origin. Then I have explained the third point, the intersection with the axis, which help us the tracing when the curve cut the x axis or y axis. Then I have explained the asymptote which help us the curve tracing while the curve is parallel to some tangent at infinity. We find the asymptote parallel to x axis and y axis. Also I have explained the asymptote in oblique form. Then I have explained the sign of first order derivative which gives us the increasing or decreasing concept of the curve, and second order derivative, the sign of second order derivative gives us the concavity and convexity of the curve. I have also explained at last the reason of existence of the curve. If we have the curve y square is equal to some function of x, and we find some value of x which gives the negative value of y square, then the curve does not exist. The existence of the curve help us in tracing of the curve. On the basis of these points, we can trace a polynomial function very easily and trace very well to find the shape of the curve. Hope you have enjoyed the lecture. Thank you.